Good evening, everybody, and welcome to our first keynote of AsTropaLooza, the Astronomy of ATL Showcase. And thank you all to our online audience for tuning in as well. We'll be taking questions from both in-person and the virtual audience. So if you have a question, fire it into the chat and we will ask it in person. So thank you very much. It is my pleasure and my honor to introduce the keynote speaker today, Dr. Misty Bentz. Dr. Bentz got her bachelor's in physics and astronomy from the University of Washington, and then her master's and her PhD in astronomy from the Ohio State University. She got a postdoc at the University of Irvine, then earned herself a Hubble Fellowship, which she then ditched to become an assistant professor here at Georgia State University back in 2010, and was promoted finally to full professor in 2021. Dr. Bentz has gotten data from the Hubble Space Telescope, and she was one of the first groups ever, one of 13 of the first groups to get the first ever observations with the James Webb Space Telescope. And to boot, she is a world expert in supermassive black holes. So without further ado, please join me in giving a very, very warm welcome to Dr. Misty Bentz.
Thank you so much for being here on a wonderful, sunny June evening on Friday the 13th. We're going to try to make this, this picture's a little bit spooky, but we're going to try to make it less spooky and more understandable for y'all. So let me just jump right in. One thing I want to note is that, especially in science, when you're not familiar, sometimes it can be hard to tell the difference between like a computer-generated image or an illustration versus an actual telescope image. And so I've tried very hard to make sure that I label all of the pictures throughout this talk. If I thought there would be any ambiguity at all. Like if it's a graph, I figure you all know what a graph looks like, but if it's an image, I've made sure to label it. And so starting with this first image, which is a simulation, and you might recognize from the movie Interstellar. So let's start with some basics. First of all, what exactly is a black hole? Some of you may know this, but for those of you who are a little unsure, let's start with something even more basic than that. Pausing for the moment. I feel like I should have like a little shoe routine. Oh yeah, this is I actually took this picture. This is a picture of the recent lunar eclipse that happened back in, was it April, I think? I don't know. It was 3 o'clock in the morning and I was standing outside with my tiny telescope is all I know. So that was one of my images from my telescope. Okay. So before I actually tell you what a black hole is, I have to remind you or maybe educate you on something, which is that the universe is filled with a lot of things, right? It is filled with planets, it's filled with stars, it's filled with galaxies, and everything in the universe that has mass, and this includes puppies and kittens and you, everything that has mass actually slightly deforms space around it. And so right now, you are deforming space-time, which is the name we give to basically the graph paper of the universe. So space-time is just the length, the width, the height, and time, the axes that we have on our graph paper. And you are deforming space-time just by existing, basically. And the sun is deforming space-time. It's a massive object. And it's a beautiful, massive object. And I have pictures of it from my small telescope as well. I don't have them as the background on my laptop, because it's not scrolling through many images, but I do have, it's actually about the same size in the picture because, as you might know, during an eclipse, a solar eclipse, total solar eclipse, the moon will fork out the sun, right, just barely. So it appears about the same size. And if I was to do some science with the sun, I could actually measure the positions of stars around the side of it during a total solar eclipse and see that their positions are distorted. And that's because of the distortion of space-time that the sun does just by existing, okay? All right, now it gets more fun when you go to even more compact objects than the sun. So if you take the sun and you evolve it forward 4 billion years and it puffs off its outer layers like the caterpillar from the caterpillar that blows the smoke rings in Alice in Wonderland, right? So, so the sun will do that in about 4 billion years. It will lose its outer layers, it'll puff off smoke rings, and the core will be left behind. And the core is much more dense than the sun as a whole. And things that are more dense deform space-time more. So when the sun reaches the end of its life and puffs off its outer layers, it will leave behind a core that distorts space-time even more strongly. So if there are humans around in 4 billion years, they can measure that deflection caused by the sun's core, and it will be even more strong. If you were to take something like the sun and squish it down to the size of the Earth, or even smaller, like the size of Atlanta, then you get something significantly more dense. It distorts space-time more. We call this a neutron star, and some very massive stars leave these behind in their core when they reach the end of their lives. Now, the most dense thing we know about in the universe, the most squished down thing we know about is a black hole. It causes the ultimate distortion of space-time. And in fact, some people view it as being like a rip in the middle of space-time. It's still at a specific point. There's still stuff there, but anything that goes in can't come out is the basic idea. Okay. All right. I think all our technical difficulties are solved, so we can move to a new slide. And this is my attempt to convince you that the name black hole is just the worst name ever, because it's incredibly misleading based on our colloquial understanding of certain words. So for example, if you think of a hole, you think of something like the picture here, right? You think of a hole in the ground as a place where material has been removed. It is empty. But I just told you a black hole is a squished down compact object. It is not empty. It is literally the most full thing that you can have in the universe. So that's just not a helpful word, right? And the other issue here is that when we think about black, for example, I'm wearing a black jacket, it has black pigments in it. If you use a black crayon or black paints, those are pigments. That's a color. Black holes have no color. And so that is also misleading. They are not black, they're actually invisible. You just can't see them. And so I propose that we should not call them black holes. Maybe we should call them invisible fullnesses, which is a mouthful and is never going to catch on, but I keep trying. Okay, so what do they look like? This is what a black hole looks like. It's invisible. That's all you're ever going to see of a black hole. And some of you in the audience may be squinting at me saying, hey, what about all those news articles I saw a couple of years ago with the first picture of a black hole? Do we remember that maybe in the far reaches of our brains? You may have seen something like this. This is an image from the Event Horizon Telescope. And this was called the first picture of a black hole, but you're not seeing the black hole here. The black hole is invisible, and it's in the middle of the donut where you don't see anything. What you're seeing is very hot gas that's very close to the black hole that wouldn't be behaving like this if there was no black hole there. So you are seeing the effect of the black hole on gas. You're not seeing the black hole itself. And you're familiar with doing this every day when you look out the window when you're deciding what to wear, because you don't see the wind blowing. You see the trees moving in response to the wind. You don't actually see a mass of air moving across your yard. And so the wind, you see the effect of the wind, not the wind itself. And with black holes, it's the same thing. We look for the effect on objects around it that we can actually study with our telescopes. Because telescopes they can't see invisible objects. And so we have to look for things that glow. All right, one really good example of how we do this is by studying our own supermassive black hole. So this is the black hole in the center of our galaxy, the Milky Way. If you look in the center of those red crosshairs on that picture there, and you zoom way in and you take picture after picture after picture after picture over decades in time, what you'll see is that the stars are moving around and they're actually orbiting the center of the galaxy, right? And so the animation that's running here, and if you watch the timer, you'll see that it starts in, I think it was 1995. There it goes. Yeah, 1995 is the beginning here. You can see how these stars have changed position as a function of time. And some of them have been monitored long enough to complete a full orbit around the center of the galaxy. Now, this is all well and good, but the thing that's super exciting here for astronomers is that they're not supposed to be going this fast. If all you can see is what's actually there in the pictures, they should be going a lot slower than they actually are. However, that little star shape is marking the point they're all orbiting around. And because of how fast they're going, we can say that there's something sitting at that point that has a mass that's 4 million times the mass of our sun. That's required to fling them around at these super high speeds in order for them to make these orbits as quickly as they are. And so that's how we can learn about our own supermassive black hole. And in fact, this work is so important that it was awarded the Nobel Prize in Physics in 2020, which is super great to have black hole science be recognized that way. Okay, so black holes are extreme objects and they cause extreme things to happen around them. But in fact, they're really, really simple. There's not that much that we can measure about them or characterize for them. They don't have colors. I told you that already. They don't have temperatures. They don't have chemical compositions. They don't have magnetic fields. They don't have brightnesses. All of these things we usually use to classify stars and galaxies and things like that, we cannot use on black holes. But I have mentioned one characteristic that they have. They actually have three, but the first one you might have picked up on already, and that is the mass, right? So I said that they're squished down objects made of stuff, and that's why they distort space-time. And that stuff is the mass that makes up the black hole, just like there's mass that makes up you or your dog or the planet or the sun. And we, in fact, find that black holes come in different mass ranges, and this is how we subdivide them. I'll start with the ones that I like most, the supermassive black holes at the bottom. So that includes black holes like at the center of our galaxy, which has a mass of 4 million times that of the sun. And that's on the small side. So supermassive black holes range in mass from about 1 million solar masses up to maybe 10 billion solar masses, right? So they are very, very massive black holes. And we find these at the centers of galaxies. Intermediate black holes are a little bit below that. They're from maybe 100 to 10,000 or 100,000 solar masses. We have a hard time finding these for a variety of reasons. They have a lot of lookalikes, and they don't affect things around them as strongly as the supermassive black holes. So they're a little hard to find, and we're not convinced we know exactly where to look for them yet, which makes it harder too. So we're working on these. We've found a couple candidates, but not a ton. We expect to find more, and I'll talk about that very briefly at the end of the talk. And then stellar black holes, these are the ones that are made when very massive stars reach the end of their lives. They blast off their outer layers in a supernova explosion, and there's enough left over in the core to just collapse in on itself infinitely into an infinitely small object, into a black hole, right? And so we find these in our galaxy generally in places where a star used to live and is now dead. And we have found several of those, but none of them are very close to us. So you don't have to worry about any black holes coming along and sucking you up because they are all very far away. All right, so supermassive black holes we'll mostly focus on in this talk. Spin is the next property. So most things in the universe are spinning. The Earth is spinning. You all are familiar with this, right? As we see the sun appear to move across the sky and go from, sunrise to sunset, that is the effect of the Earth spinning. What you could see, I could show you a movie of the sun spinning, and you can see that most easily about now when there's lots of sunspots on it. You can actually see them moving across the front of the sun. Sometimes they go all the way around the back and hold themselves together to come around to the front again, which is really cool. Our galaxy is spinning. Everything in space is spinning at some level. It's just a question of which direction it's going, whether it's going fast or slow. Some black holes we know of are spinning very, very rapidly. Some are spinning rather slowly. And then the direction here is relative to something else. If it has something around it, like a disk of material, are they going the same direction? We call that prograde. If the black hole is going in opposite direction from the gas or whatever it is, then we would call that retrograde. It's retro, super cool, right? And finally, electric charge is potentially something we could measure for a black hole. Nobody knows how to do it. If they did, it would probably be a really boring result because every large object in nature is electrically neutral. So the answer they'd measure would be 0. But it's possible. And people are thinking about this because it's always good to test your assumptions and make sure that you actually understand nature the way you think you do. So people are working on it, but we haven't made much progress there. And that's all, folks. If you measure these things for a black hole, you know all there is to know about that black hole, which is fantastic. So they're simple. These are hard to measure, but they're still simple. All right, so I want to very briefly take you on a short journey here, and that is because we often see facts laid out in a textbook as if they're just things we've always known, right? And yet, and all the things I just told you are things we know now, but that doesn't mean we knew them all that long ago, actually. And in the terms of black holes, you might be surprised at how short the history actually is, or how long it is if we talk about the first data point here. So as far as we know, the first person to have the idea of a black hole, and he actually called them dark stars, this was John Mitchell back in 1783. He was a country rector at a parish in the UK. He had extra time to sit around and think about sciencey things and write letters to friends. And in one letter, he proposed an object that had an escape velocity that was faster than the speed of light. And he called that a dark star. This is actually basically what a black hole is. It's escape velocity, the speed you have to be going to get away from it. Their escape velocity is larger than the speed of light, and the speed of light is the fastest that anything can go. So if you have to go faster than that to get away, but it's impossible to go faster than that to get away, there's no getting away from a black hole. So he had this idea, and then nothing happened for a long time until this man, some of you have probably heard of, called Einstein, came along and published his theory of relativity. And 1 year later, a man named Carl Schwarzschild actually used that theory to predict that black holes exist. So this is the first mathematical prediction. And over the next few decades, there were various people who were taking observations of the night sky at different wavelengths and seeing effects of black holes, although they didn't really realize what it was they were looking at yet. And they were seeing this in the radio. They were seeing this in visible light. We were finding out that some objects were way more luminous than we thought was possible, and they were really far away. Around 1967, that terrible name black hole was proposed, and it stuck. And we've been using that name ever since. And I really wanted to make this slide because of this next point. We didn't have the first ironclad evidence for a black hole until we had the Hubble Space Telescope. So NASA's Hubble Space Telescope in 1994 provided the first confirmation of a black hole based on its effects on the material around it. We did not have the tools before that to do this. And Hubble has an amazing legacy to devote to the history of black holes. And then in 1998 is when Andrea Ghez published the first ironclad evidence for a black hole in our Milky Way. And she's the one who had made that animation I showed you before of the stars moving around in the center of our galaxy. So you can see that it's not that long ago that we could really say that black holes are not science fiction, they're actually science fact. So what have we learned since then? Well, we've learned that all galaxies have a supermassive black hole. Galaxies come in many different shapes and sizes and colors, and you can see some different examples on this screen here. And all of these have a supermassive black hole at the center. There is an exception, the little irregular galaxies, like the little blue train wreck at the bottom there. Like, where is the center? Where would we even look to find the black hole? Is there something there? We still have a lot of questions about those, but all the rest of them, as far as we can tell, have supermassive black holes at their centers. And this is, again, something that NASA's Hubble Space Telescope helped us to learn. Not only that, but the galaxies and the black holes scale together. So when you have a bigger galaxy, you have a bigger black hole. When you have a smaller galaxy, you have a smaller black hole. And this is weird and not expected. And you say, why? That seems normal. Well, remember that a black hole is something that's squished down so small. It's smaller than our solar system. It's smaller than the sun. It could be an infinitely small point in space, right? Galaxies, like our galaxy is 100,000 light years across. That's huge. Why should something so big know about something so small, right? And the mass that a black hole contributes to its galaxy is also quite small. It's at the least 1/1000th of the total mass of the galaxy. So it doesn't have enough gravity to do anything to the rest of the galaxy. So it's weird that they seem to grow with each other. And we're still trying to figure out exactly how that works, although we have some ideas. So for example, we see that black holes can grow over time. We can see this happening in a couple of different ways. We see galaxies that smash together in the sky. So there's an image of a galactic train wreck here on the right. That's from the Hubble Space Telescope. And then there was a computer simulation that sort of showed you the messy destruction when two galaxies run into each other in a head-on collision, right? And if each of those galaxies has a black hole in the center, presumably once the dust settles, those black holes will find each other and smash into each other. And when they do that, you start with two black holes, you smash them together, and you have one larger black hole in the end. Okay? And so you can grow them that way. We call it through mergers. Or you can grow a black hole by dumping material onto it. So if anything that goes in stays in, right? Can't come back out again. And so you can just dump a whole bunch of material and feed your black hole and slowly grow it over time that way. So we know of at least a couple ways to grow your black holes over time. Now, I do want to make an important point here. Black holes don't suck. They are not cosmic drinking straws. They are not cosmic vacuum cleaners, and it's just gravity. So I was very deliberate with my words on the previous slide. You have to dump material, right? I didn't say they suck material in. And here, what you can see happening is a star falling into a black hole. It's not being sucked in, it's just falling in. And in this particular animation here, this is what we call a tidal disruption event. So the star is falling into the black hole. It's getting stretched into a long, thin spaghetti noodle, and then it's getting slurped up as all of the material falls in. And we can see this happening in some galaxies. In fact, the Hubble Space Telescope just saw this happening. This is an article from last month where a tidal disruption event was caught, and it's not at the center of the galaxy. That's a little weird. So it could mean that this galaxy ate a smaller galaxy some time ago, and the black hole from that smaller galaxy hasn't made its way to the middle to find the bigger black hole yet. But we're still trying to figure out exactly what this particular result means. Okay, last point about they don't suck, it's just gravity. If I was to take the sun and I was to magically, I can't do this, but if I was to magically squish it down into a black hole with just a snap of my fingers and nothing else changed, the Earth would just keep orbiting around it like nothing had happened. It would get cold and dark, yes, but our orbit would just continue exactly the same as it is. And that's because the gravity is the same if the mass stays the same and if the distance between the objects stays the same. It doesn't matter what the objects are. Gravity doesn't care. And so gravity is not something to be scared of unless you're on a very tall building and you're very close to the edge, then you might be a little scared. But in this case, it's just gravity. All right, so I've shown you some evidence that black holes should eat stuff, right? We dump things onto it, they should eat it. That tidal disruption event was a black hole eating a star. And in fact, black holes are very messy eaters. You can see, a scientific example of that on the right, where we have an image from the Hubble Space Telescope, and you see two very strong collimated jets being shot out of the center of the galaxy, and in fact, plowing into the material around and causing a shock wave on the bottom right there with that blue glowing arc. So that's a shock wave from the jet slamming into material that's out there. And this material that's coming out is stuff that was in the process of being eaten by the black hole. It didn't make it all the way in, which is how it manages to get away. That's an important point. And so it's like Cookie Monster when he eats a cookie. If you've seen this process recently, you know what happens to the cookie, right? It goes everywhere, crumbs and shrapnel everywhere. Black holes do exactly the same thing. They're extremely messy eaters. And in fact, this is one of the ways we think that black holes can influence their galaxies that might be helping explain why the galaxy and the black hole know about each other, why they're growing together. Because clearly the black hole can affect the galaxy in these kinds of cases. And in fact, we can see that they can affect not only the galaxies that they live in, but the galaxy on the left there, that's a radio galaxy. The pink there is the radio observation from the National Science Foundation's Very Large Array. And you can see that those jets stretch way outside of the galaxy into the environment around the galaxy, and even at several times the size of that galaxy, right? And on the right, you see another example. Here we have the pink are the radio jets, so that's from the National Science Foundation's Very Large Array again. The blue is an X-ray observation from NASA's Chandra X-ray Space Telescope. And then the yellowish color is the visible light from NASA's Hubble Space Telescope. And so this is a cluster of galaxies. The galaxy at the center is driving the pink jets. And you can see the pink jets have punched holes in the X-ray emitting clouds of gas that are in the center of the entire galaxy cluster. Right? So black holes are simple objects, but they're so extreme that they can affect huge areas around their environment, which is pretty cool. And I particularly like that last picture I showed you from Chandra and the VLA and Hubble, because it that's what I thought of when I first saw this picture on the left. This is an image in gamma rays, and it was collected by NASA's Fermi Space Telescope. And the blue glow and the line along the center there, that's the disk of our Milky Way galaxy. Our galaxy is very flat and thin, and we're inside it. And so when we look towards the center, we just see this pancake across the sky. So that's the disk of our galaxy. And rising above and below, you see these bubbles of gamma rays that are coincident with the center of the galaxy. And I said, I know what that is. And eventually, a lot of other people came around to believe that was probably what was going on too. This looks very much like bubbles, crumbs from our supermassive black hole the last time that it had a snack, which is really cool to see these echoes of its last little feeding frenzy. Okay. So we've got all sorts of interesting things that we've learned with the telescopes that we've had in space. A lot of these are run by NASA. One of the most recent telescopes we've launched is NASA's James Webb Space Telescope. Some of you may remember the excitement when it first launched on Christmas Day, that I got up at 6 in the morning and I had my cocoa and my Christmas present was watching JWST launch. And this was one of the first images that was released. This is a deep frame of a galaxy cluster. And you can see the mass of all of these different galaxies in the cluster distorting the pictures of the background galaxies behind the cluster. So you see these arcs and swoops across the image. Those are all background galaxies. The light comes through the cluster and gets distorted like a funhouse mirror from the mass distortions of all those galaxies in the cluster. And then we get this funny looking view on the other side. Sometimes we get more than one picture of the same galaxy. It's actually a really cool effect. And people study that in great detail. But what you can see here is just an endless number of galaxies. Different colors, different sizes, different shapes. Everything in this picture, except for the objects with the blue spikes, everything in this picture is a galaxy. And each of those galaxies is filled with hundreds of billions or trillions of stars and a supermassive black hole. So we have a lot to explore. This is one picture of the sky, one little tiny snapshot in area, and then you take that and you multiply it all the way around the sphere that we live in. And there is a lot of space out there for us to learn about. So it's a really exciting time. We have a whole bunch of questions that we're trying to solve in black hole research. I like to call these my supermassive questions. The first one is, where did these black holes come from? Like, how did they get there in the centers of the galaxies? And when did they start? And what's going on here? Which came first, the galaxy or the black hole? And, we're starting to make a little more progress on this with JWST. But if you look at the headlines here, you might realize that progress is messy. We find a lot of things that seem contradictory, or maybe it's not what we expected. And that's how science progresses, like bumping into things into the dark until you eventually figure out what it is that you're doing. That's how we do things in astronomy too, is bumping into things in the dark a lot. So we're working on that. Another question, how do the black holes grow? I gave you some brief examples, but the details, we want the details here. What physically is happening, how much goes in, how much doesn't make it in and comes out as crumbs. How often do black holes eat? Do all black holes eat? Do all black holes go through mergers? Does it depend on where they live, right? There's a lot of questions you can ask about this. And again, we find that, astronomers are confused. Astronomers stumped, right? That's always the headline. The astronomers are stumped. So we're making progress, one observation at a time. And finally, really what's going on when these black holes are affecting their galaxies, and how are the galaxies affecting the black holes themselves, right? These are important questions to understand why galaxies look the way they do, including why does our galaxy look the way it does today? How did it come to be like this, right? And JWST, again, is providing some illuminating answers. We have to think about this all a little bit more. So we keep collecting pieces of the puzzle, hoping that eventually we get the picture figured out. Right? And so that's one of the fun things about being a scientist. You never know what you're going to be doing each day. You have lots of questions to think about, lots of things to ponder, and sometimes really cool new tools to play with, right? So we live in a really exciting time, but we also live in a really uncertain time, unfortunately. So some of you may be aware that every year we have to set a budget for the country, right? I'm sure you have to set a budget at home too. And that process starts by the president proposing a budget request to Congress, and then Congress decides what the budget will actually be. We have just started this process for 2026, and the president's budget request is honestly devastating for science. So you can see the proposed amount of money for the NIH, for NASA, and for the National Science Foundation. These are numbers that we have not seen before. They are so low that basically 66% of NASA astrophysics would be shut down immediately. So that understandably is concerning a lot of us. And just to sort of show you what that looks like in something that might make a little bit of a bigger impact, this is NASA's current astrophysics fleet before any cuts are enacted. You can see the satellites that are up there. These are specifically for studying astrophysics. So this doesn't include climate satellites or heliophysics satellites. All of the red X's are showing you everything that will go away if this budget request stays the same and is enacted. And I think the plot just really sort of makes the point. And I have a lot of emotions and feelings about this plot, and you may too. And so if you do, what can you do? You can do something. We all can do something. You can call your US representative and your senators, the people in Congress who are supposed to be acting on your behalf, and ask them to fully fund science. Now, we like to not play favorites. We don't want to say, please fully fund NASA over the NSF or the NIH or NOAA or any of these other, right? We want all of science to be preserved because science is impactful on our daily lives and important, right? And so the best way to try to help science is to bring all the boats up together, right? And so ask your representatives to fully fund science. If you don't know who they are and you're registered to vote in the state of Georgia, you can go to the Secretary of State's website, log in, and it will tell you who all of your elected representatives are, from the city and county level all the way up to Congress. Okay? And if you don't know how to contact your representative, and that sounds really scary, there's a ton of materials to make it super easy for you. Go to planetary.org and click on Save NASA Science. They have little scripts there, like you can just literally read the script on the phone to your representative, so you don't have to think about what to say. They have tips, they have frequently asked questions to help you feel more informed. When you make these phone calls, they just say, okay, thank you, and then they hang up. They won't like ask you questions. It's not a conversation. You just call and say, this is what I want and why. Thank you very much. And so I know it seems scary. It always seems a little scary to me. I don't like talking on the phone, but it's actually not that bad. And you can call after hours and leave it on the voicemail instead. You don't actually have to talk to a human if you don't want to. It still counts the same amount. So there's something else you can do. You can reach out to your representatives who are going to be setting the budget, and you can talk to your friends and your family and your neighbors. And here I am talking to a bunch of strangers and some friends in the audience about why is science important to you, right? Talk up science, remind people why it's important to invest in science. You can be very practical. Maybe it's because every dollar that is invested in NASA results in $3 in economic benefit. You're not wasting money when it goes to NASA. You're actually boosting the economy of our country. I think that's a sound investment. If you want details on that, you can go to the NASA Economic Impact Report that was just published for 2024, so you can see all the facts. Maybe it's because NASA does a lot of research that ends up creating things that make our daily lives better. So some examples of this include things like high quality wireless headsets, which some of you may use. Includes scratch-resistant coatings for lenses. It includes the cameras in your cell phones and in digital video cameras. It includes other things, all sorts of medical devices. So insulin pumps were developed at NASA. I think that's a really important one. It includes food preservation methods and all sorts of food additives, things that go into baby formula to give them more nutritional value, for example. All kinds of technology spin-offs that you probably have never heard of related to NASA. And yet you're using them and it's improving your life on a daily basis. So another very practical reason why it's good to invest in science. And my personal favorite reason why science is important to me is that astronomy in particular, but science in general, is sort of the most human endeavor you can do. You are exploring your environment, you are asking questions and interacting and trying to make sense of it. And in a time when we're maybe turning over more of those processes to machines, I think it's important to remember our humanity and to maybe actually want to spend a little more time developing it. And science is that for me. So I hope you have your own reasons and think about it a little bit. Have some conversations about why science is important to you. All right, so I don't want to end on a bummer. I want to end with exciting things that are coming up really, really soon. This field always has exciting things going on, and we really want that to continue. The Vera Rubin Observatory, the first look images, we've been building this observatory in South America for years now. It's right there. They're like testing everything to make sure it works before it goes online, and they're going to release the first look images, first public images. I'm public here. I'm not an insider. I don't know what the images are. Monday, June 23rd at 11 a.m. Eastern Daylight Time. And they're going to have a huge reveal party for it, so you can log in online to watch. I'm sure it will be on the nightly news that night too, but join in the celebration. This is an exciting unveiling of something new. It's a new way to look at the universe that we haven't had before. And the Rubin Observatory is going to create a movie of the night sky. And so we're going to be able to see all sorts of things that change over time, and that will fill in our gaps in our knowledge and show us things we've never seen before that we have to figure out what they are now. That's part of the fun, right? And also coming soon is the Nancy Grace Roman Space Telescope, which will be launching no later than May 2027. You can see a picture of it in the clean room there. It is this close to being done. And in fact, they're on track, so they might actually be able to launch as early as fall 2026, so just a little over a year from now. And again, it's going to revolutionize the way that we see the universe around us and help us answer some of those supermassive questions I posed to you before, while giving us a whole new list of questions to ask and to ponder as well. And so stay tuned, get involved however you can, and I look forward to answering any questions you have. Thank you for spending your Friday night with me.
Thank you so much.
Do we have any in-person or virtual questions for Dr. Bentz?
This is the online audience.
I just had a question. So you said that black holes don't suck. So how, if they like turn into a black hole, our sun goes into a black hole, does that mean that other planets will just stay? Like they never go into it? They will destroy them?
Yeah. It does mean that if our sun turned into a black hole, the planets would just keep going around and around. Something would have to come push one of the planets in. So like if so we get these sometimes crackpot letters from people who are like, I have a theory about a planet hiding on the other side of the sun, and that's why we haven't discovered it, right? Like if a rogue planet came along and smacked into Earth, that could push it into the sun. Even if the sun wasn't a black hole, it could push it into the sun. But yeah, if the sun was magically changed into a black hole, we just keep going around and around. Yeah, which is pretty cool. So you could potentially have planets orbiting black holes, actually, which was an idea in the movie Interstellar, but could actually be true in real life. We haven't found any, but it's possible.
We have a question on. Oh, sorry, go ahead.
If you said almost every universe and galaxy has a black hole, does that mean they're necessary for the galaxy to exist in the stable?
They shouldn't be necessary for the galaxy to be stable, but what I think it means that since every galaxy has a black hole, is that it's a normal part of the formation process. And so it's just something that regularly happens. We do think there may be a few galaxies. We haven't found any that are really good candidates, but some people spend a lot of time looking for galaxies that may have ejected their black hole. Because if you shoot a bunch of things at each other, right, you could have two black holes coming into each other, and depending on how they find each other and which direction they're spinning and how massive they are, you can actually kick things out and stuff like that. So there is some reason to think you might be able to lose your black hole. Maybe. We might find some eventually. But it seems to be just a normal part of galaxy formation and the processes that happen. Yeah. And the galaxy would be fine if it lost its black hole. So it wouldn't like disintegrate or fall apart or anything. It might be a little sad, but it would be okay.
Let's go online and then we can go back to our in-person. We have a few questions from Juan Ramos from Oglethorpe University. So I'll do one, we can switch and I can go again. One of his questions is, do black holes die? And if they do, what will there be any way to analyze anything from it?
So this is a great question. It's a question that scientists have as well. There's one potential mechanism for black holes to die, but we don't actually know if it's happening because we can't measure it. So right now it's just an idea. So black hole evaporation is the term. And it's a thought that you might actually have black holes losing little bits of themselves very slowly over time. And the process is slower and slower and slower the more massive the black hole is. So if you had some tiny microscopic black hole, it could go relatively quickly. We've never discovered any of those. There were fears that the Large Hadron Collider would create these kinds of black holes. That never happened and was never going to happen based on the physics. But we've never discovered any of these. We have no evidence that they exist. But if black holes evaporate, those would be the ones we could potentially use to test it. However, supermassive black holes or even stellar black holes, they take longer than the age of the universe to evaporate. So they're so slow that there's no hope that we could ever actually see that happening. So it's an idea that we will probably never be able to test, unfortunately.
Isaac,
Yeah, so I wanted to ask a similar question to what asked just now. So I know that stars can end up as a black hole or as other compact objects, depending on their mass, initial mass. But I wanted to ask if there are some theories that also predict the evolutionary transfer of black holes depending on their masses.
So the question was whether there are evolutionary tracks predicting what happens to black holes at different masses? No, because in general, if they have nothing particularly around them, they don't evolve. They're not actively doing anything when they're by themselves. The only way they change is if something falls in and changes the mass. And so they could go through a short burst of activity where they eat a snack and shoot out a bunch of crumbs. But as soon as the snack is gone, they just sit there and they're not actually doing anything. So I wouldn't say black holes actually evolve at all. Yeah, they can grow, and that would come in fits and spurts, but that's as close as they get to evolving.
We have another question from online, from the same person, Juan Ramos. I'm going to guess that you get these questions as often as I do when I say the word black holes. With black holes existing, would there also be such a thing as a white hole that repels objects? If so, would they instead be events such that the Big Bang is one of those events creating the whole universe?
Yeah, this is a really fun idea that you might get white holes along with black holes. This is another one of those ideas that we have at the moment no way to test, and so we can't actually say for sure, but it's a fun one to think about because it has a lot of really interesting consequences. And you put your finger on the one that I like to tell people about, which is the Big Bang, right? If you, instead of having things collapsing down into an infinitely small point, have things shooting out of an infinitely small point, it kind of sounds like the beginning of our universe, right? And if that's what the Big Bang actually was, then it raises the interesting possibility that anytime you create a black hole in our universe, maybe you create a white hole in another universe somewhere else. And so then you end up with this Swiss cheese, different levels of black holes, right? Black holes inside black holes inside black holes level of multiverses, which starts to make your head hurt after a little bit, but is really fun to think about for a short period of time. But at the moment, they're just fun things to think about, and we have really no way of going out and looking for them or measuring them.
Any other in-person questions?
So you think a lot about the relationship between black holes and their host galaxies. And I'm wondering, how normal is the Milky Way? Is our relationship to our black hole kind of normal, or are we a weirdo?
Yeah, the question is the Milky Way a normal galaxy in terms of its relationship with its black hole, or are we maybe an outlier or a weirdo in some way? In general, as best we can tell, because it's hard to study our galaxy from inside it and make the same kinds of measurements that we make for other galaxies, but as best we can tell, we're normal. There's nothing special about us. This is usually the answer in astronomy, is that we're not really weirdos. We're just like everybody else, right? That's what we tell people anyway. But in this case, yeah, the Milky Way seems like just a normal galaxy.
One more fun question to close this out. From online, from Mr. Ramos. When we watch something being spaghettified, is it actually being stretched, or is it that when the light escaping makes it look like that to an outside observer?
Oh, no, it's definitely being stretched, because you can actually take that star and pull it apart to create a disk of material around the black hole. So you can create an accretion disk, and all of the stuff in that accretion disk is gas and plasma that was originally inside the star. So you actually shred the star, you rip it apart, temporarily create a disk where the inner edge is feeding the black hole, the inner edge is falling in. Some amount of it is getting shot out in the process. And then eventually you eat it all up and it all goes away. So yeah, you are literally pulling it apart. So it would not be fun to fall into a black hole. But as I said, we have no reason to worry that that would happen because they're all super far away. So.
All right, and with that, let's give Dr. Bentz one more round of applause.
Thank you all
so much for coming physically in person, and thank you all so much online. This was recorded and it will be posted. You can view it at any time afterwards. So thank you, everybody. That wraps it up for the second day of AsTropaLooza. Thank you.
that looked like